In the poll of last week, you chose the experiment decomposition of hydrogen peroxide. So today we will be talking about just that. Hydrogen peroxide, H2O2, is a chemical compound commonly recognized for its role as disinfectant and bleaching agent. Now, at higher concentrations, hydrogen peroxide also serves as a powerful mono-propellant in rocket propulsion systems. In this video, we will be exploring the relationship between hydrogen peroxide's decomposition rates at various concentrations and its application as a rocket fuel. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. And if you like this video and want to see more, make sure to subscribe. If you want to influence next week's poll and choose what element we will discuss next, make sure to fill it in. Now, you may have seen this experiment already in one of the celebration videos. And the goal of this experiment is to observe how the decomposition rate of hydrogen peroxide varies with its concentration when catalyzed by manganese dioxide. By understanding this reaction, we uncover fundamental principles of chemical kinetics and catalysts. The experiment also serves as a precursor to understanding how high concentration hydrogen peroxide, such as 70%, functions as monopropellant in rocket propulsion systems. At some point in the future, I would really love to demonstrate this, but right now, unfortunately, we can't yet. Now, hydrogen peroxide decomposes naturally into water and oxygen, releasing heat. Below you can see the formula. Now, this reaction is typically very slow, but it can be accelerated with a catalyst like manganese dioxide. Now, the catalyst provides a surface for the reaction to occur, lowering the activation energy required for decomposition. Now, it's very important to note that the catalyst is not consumed in the reaction. Now, after the reaction, there are several products left. First of all, water, H2O, which remains in the liquid or the vapor phase depending on the heat. Second, we have oxygen gas, O2, released as bubbles. Third, we have heat, and that drives the reaction forward and can vaporize water at high concentrations. Now, like mentioned, we were going to use different concentrations of hydrogen peroxide. Now, why does that matter? Well, the concentration of hydrogen peroxide determines the number of H2O2 molecules available to react. Higher concentrations can lead to faster reactions, greater heat production, and more oxygen released. Now, this experiment can be pretty dangerous, so it's important to use safety precautions. Make sure to use safety gear, goggles, gloves, and a lab coat if you're trying to perform this at home. So, we're going to need several things when we do this experiment. First of all, we need hydrogen peroxide solutions. I use 3, 12, and 18%. We will need manganese dioxide powder in several amounts. We will need 3 small glass flasks or beakers if you like. We will need some measuring tools to make sure that we have the correct amounts of hydrogen and a small scale for the manganese dioxide. Now, the procedure by itself is very simple because we're just going to dump the manganese dioxide into the hydrogen peroxide. For each experiment, you will use the right amount of milliliters of hydrogen peroxide and vary the concentration. The recommended amounts for manganese dioxide are, for the 3% hydrogen peroxide 50 milliliters, 0.25 grams of manganese dioxide. For the 12% hydrogen peroxide, 25 milliliters, 0.25 grams of manganese dioxide. For the 18% hydrogen peroxide, 25 milliliters and 0.375 grams of manganese dioxide. So this is how we're going to do the experiment. First, we measure the 50 and 25 milliliters of hydrogen peroxide and pour it into an Erlenmeyer flask. Then we weigh and add the specific amounts of manganese dioxide and add that to the Erlenmeyer flask. Now, at higher concentrations, the reaction becomes more vigorous due to increased availability of H2O2 molecules. The heat generated in the 18% reaction may be sufficient to produce noticeable steam. Now, since I'm quite an amateur chemist, the results were actually not meeting the expectations. So what are the expected results? Well, for the concentration of 3%, the reaction rate is probably going to be slow and gentle. The foam bubbles will be minimal and the heat output will be slightly warm. Let's start with the first experiment. For the 3% hydrogen peroxide, you can see that the reaction rate is indeed slow and gentle. The foam bubbles are indeed minimal and the heat output is slightly warmed. You can see some small vapor, but you cannot see steam. For the 12%, the reaction rate will be moderate and noticeable, the foam and bubbles will be significant, and the heat output would be warm and noticeable. Now here we got the 12% test. As you can see, the reaction rate is moderate and noticeable. The foam bubbles are quite significant, and the heat output, well, we can actually see steam coming out of the flask. Now, for the 18%, we expect a rapid and vigorous reaction rate, and the heat output will be very high. Okay, so here we got the 18%. But this is not rapid and vigorous. This is not intense foam production. And this is not high heat output. So what did I do wrong here? Well, I did the same thing wrong that I did wrong in the tests for my celebration video. I used a too small surface. As you can see, I used a smaller and smaller Erlenmeyer flask, which reduced the surface. Since it's a surface reaction, which I explained at the beginning, it means that the bigger the surface you use and the smaller amounts of solutions you use, and there you pour into the manganese dioxide, the effect will be bigger. And this is what I did wrong. So the 18% wasn't as rapid and vigorous as you would expect because I used a smaller Erlenmeyer flask. And the bad thing was that I now also used up all the 18% hydrogen peroxide that I had. But luckily I still have this footage from the celebration video, which was also 18% hydrogen peroxide. Now, to show what would happen if you would use the 12% on a bigger surface, here is some footage from 12% hydrogen peroxide when you use a smaller Erlenmeyer flask. As you can see, the reaction is a lot stronger. So here you can see, in this case, surface really matters in this experiment. So these were the tests that I prepared, but you can already see that with 3, 12 or 18%, the reaction rate is quite significantly different. Now you can imagine that at concentrations of 70% and above, hydrogen peroxide becomes a powerful chemical fuel, and this is known as a mono-propellant. When decomposed in the presence of a catalyst like silver mesh or manganese dioxide, the reaction occurs almost instantly, releasing oxygen gas and converting water into superheated steam. So here you got the formula for that, and the reaction dynamics will look something like this. The heat output, the decomposition temperature, will exceed 600 degrees Celsius. Now the thrust mechanism that will then happen, well, the rapid expansion of the oxygen and the steam generates high pressure exhaust, providing thrust in propulsion systems. Now in the reaction speed, the reaction is nearly explosive, with all the H2O2 molecules decomposing in a fraction of a second. And that is what we used it for. The 70% hydrogen peroxide has been used in auxiliary power units like the Bell X-1 rocket plane. The energy from this reaction is sufficient to power small rockets or provide thrust for attitude control system in spacecraft. But you have to realize that there should be safety considerations. 70% hydrogen peroxide is highly reactive and dangerous. It requires specialized equipment to handle it, rigorous safety protocols to prevent uncontrolled decomposition, and catalysts designed to withstand extreme temperatures and pressures. This experiment demonstrates how concentration influences the decomposition of hydrogen peroxide and the role of manganese dioxide in accelerating the reaction. While 3, 12 and 18% solution produce increasingly vigorous reactions, 70% hydrogen peroxide highlights the transition from a laboratory reaction to a practical fuel for rocket propulsion. This progression illustrates the power of controlled chemical reaction in engineering and science. And that concludes this episode. For now, if you think I missed anything, make sure to leave it in the comments. And if you like this video, make sure to subscribe.